about combined loading, but in combined loading, there is going to be nothing new. It's just going to be all the previous concepts combined together. So that's going to be our chapter 9 about the combined loading. So yeah, so chapter 9 would be about combined loading, where we'll have different members, but we'll use all the concepts we have learned in this subject together, all together. But we can just revise yield criteria a little bit. So now we know there are two type of materials. There are ductile materials and there are brittle materials. So ductile material, this is how the stress strain curves looks like. So in a ductile material, when you keep on applying load, you will have yielding. And after yielding, you will have some extensive amount of plastic deformation, and then it will fail. But for a brittle material, if you keep on applying a uniaxial load, you will have yielding and then a sudden failure. So in ductile material, you can see the plastic deformations before the failure. So you get a little bit of warning. In ductile material, it's yielding and abrupt failure. So you don't see a lot of plastic deformations in a brittle material. And also, these stress and curves are under a uniaxial testing. So if you only have a uniaxial load, you can predict yield of any material pretty accurately. But if you have a complicated loading condition, then it gets harder and harder to predict yielding. So yielding is a point where after that you will have plastic deformation, and we don't want that in all our machines, buildings, bridges, whatever we design. We design it to have stresses lower than the yield point. So if you have stresses higher than the yield point, then it will have permanent deformation. If it's a brittle material, it could fail. So we don't want that. So all our members, we have to make sure that the stresses in those members are lower than the yield point. So for a uniaxial test, coupon test, it's very easy to predict yielding. But if you have a complicated scenario, then it gets harder and harder to predict yielding. So that's why we have this chapter. That's why we have yield criteria. So we have different theories which kind of predict yielding, but under given loading condition. So for a ductile material, you have different theories. For brittle material, you have different theories. So for a ductile material, we talked about Tresca and we talked about von Mises. So Tresca, this is the yield criteria. So this is all you have to remember for Tresca. So in order to predict yielding in a given loading condition, we already know the yielding for the material, but we can calculate the stress 1 and stress 2, and then we can compare it using these formulas. And if stress 1 minus stress 2 or stress 2 minus stress 3 or stress 3 minus stress 1, they are more, the stresses are higher than the yield, then we will observe yielding, we will observe permanent deformation, or if it's a ductile material, we may observe fracture after if the stresses exceed the yield point. So that's how you check that if a member is going to yield or not. And we have to keep those stresses lower than the yield stresses. So this was Tresca theory. And we also talked about von Mises. So this was yield criteria for the von Mises. So similar, you can calculate stress 1, stress 2, stress 3 from our stress element, and we can compare it with the yield criteria, and we can figure out if a given loading condition will observe yielding or not. If it's a brittle material, then we can use Coulomb's theory. So this is the formula for Coulomb's theory. So all we have to do is that we have to individually check our stresses with the yield criteria. So we're gonna just talk about yield surfaces. So yield surface, just like a Mohr circle, is a graphical representation of the stresses. So we can just visually see the stresses, and we can extract any amount of stresses. We can extract maximum shear stresses, maximum normal stresses without using the equations. So yield surface is also graphical way to figure out if we will observe yielding or not. So we can just plot these stresses, stress 1 and stress 2, on x and y axis, and then we can just draw this shape. So this shape is specific for a given theory, so I'm going to just write it down. So if your point lies inside this stress 1, stress 2 point lies inside the shape, then it's safe. It's not going to yield. But if it lies outside, then it's going to yield. So for example, in this case, you have 3 points, A, B, and C. So A lies inside the box, B lies inside the box. So these 2 points will not observe yielding, but the C point will observe yielding. So this is what we will do, and then we will start example 11.3, which is the last example of this workbook. And then we will talk about combined loading, which is nothing but all the concepts combined. So that's the end of this subject. All right. So this is what we were talking about in example 11.1, right? So we know the material is given, which is A36. We know this material is steel. We know this material is ductile. And we also know the yield stress of this material, 250 megapascal. So this 250 megapascal is that stress when this A36 material is loaded in only one uniaxial load, then we know it will yield at 250 megapascals. But under different loading conditions, we don't know when it will yield. So that's what we are going to figure out in example 1. So we have been given this one stress element. We draw a circle. Also, we calculated the maximum normal stresses, which are also called principal stresses, stress 1 and stress 2. So we have already calculated this stress 1 and stress 2 from this stress element. So now we have stress 1 and stress 2. Now what we will do is that we'll use this information and the yielding information, which is a material property, and we'll try to figure out if in our case we will observe yielding or not. So this is what we did. We rotated the stress element to get maximum principal stresses, which is this stress element. So the maximum stresses we are going to get is, this is 146, I guess, 146 and 126. These are the maximum stresses we'll get. And since it's a ductile material, so we'll use Tresca theory and von Mises theory. So this is what we did. We used these formulas, and we figured out that under Tresca, we are getting 272. So under Tresca theory suggests that this stress element might yield. So this will yield according to Tresca. We also use von Mises. So von Mises theory suggests that it will not yield. So two theories are giving us a kind of different results, but it's so we don't know. But most likely, experimental studies suggest that von Mises is more accurate theory. So what we can do, we can draw yield surfaces. Okay. Oops. So we had last time, this is what we did, right? We had Tresca and we had von Mises. So Tresca says our stress is 272 and it suggests yielding, right? And we also had stresses which we determined from von Mises, and the stresses we got from von Mises was 230 megapascal. So it suggests that it will not yield, right? So we can get the same information from yield surfaces as well. So just like Mohr circle, which can give us different stress configurations, and we can extract maximum normal stresses and shear stresses, we can also draw yield surfaces to visually see if the failure will happen or not. So we know that these two stresses, stress 1 and stress 2, are responsible for determining the failure. So this is what we will do. We can just graphically do the same thing. So we will have stress 1 here and we'll have stress 2 here. So we'll draw yield surfaces. So yield surfaces are same. They always remain the same. They don't change. So for example, we know if stress 1 goes to yield point, we're going to have failure. So this is positive. This is positive. this should be negative, this should be negative. So if yield is negative yield, you'll observe failure. If you have yield of stress 2 point, you'll see failure. If you have yield of negative, you will have failure. So all you have to do is you have to draw straight lines. So you can maybe kind of remember because it's going to be the same all the time. So this is Tresca yield surface. This is called Tresca yield surface. And it's always going to be this shape. It's always going to be this shape. All we have to do is our stress one was 140 megapascal, right? From last example. Our stress 2 was negative 126 megapascal. So we have to draw these as stress 1 and stress 2 coordinates, which is 140 and minus 126. So this is Tresca yield surface. You can kind of remember this. Yield, 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 yield. And for the first coordinate, it's a box, and then you have to draw a straight line. So this is a yield surface for Tresca. I will also draw a yield surface of von Mises. So the yield surface for von Mises is a parabola. It passes through the yield points, but so this is von Mises yield surface. And I can also draw the other Coulomb yield surface. So this is Coulomb yield surface. So Coulomb yield surface is just a box. So this is Coulomb yield surface. And I mean, that's how it is. They don't change, so you can kind of remember this, how these yield surfaces are. But we're gonna plot this 140 minus 126 here. So if I see, if this is yield is actually yielding is happening at 250, right? So 140 would be somewhere here, and then I have to go negative 126. So it should be this point. This point is actually 146 and 126 negative. That's the point. This is our point. This we got from these stresses, and these stresses we got from stress element. So we can see it's beyond the Tresca yield surface. So according to Tresca, it's failing, but it's under the yield surface of von Mises. So according to von Mises, it will not fail. Even if it's difficult, you can just like remember this. That it's always gonna be the same shape for Tresca, von Mises, and this is for Coulomb. So this is just a visual way to see, but you can also use equations formulas to figure out if we will observe yielding or not. So now, I mean, like now we can combine everything which we have learned in this subject, and we're gonna do this. So we have this one example, which is example 11.3. So it's kind of comprehensive example which takes into account of all the concepts we have learned throughout this subject, and it's going to be the same in the combined loading case as well. So like congratulations, we have like kind of finished this subject, but we're going to just like now do combined loading where we'll use all the concepts we have learned over all the chapters, and then we're going to do some exercises. So if this is okay, we can start example 11.3. So example 11.3. So chapter 10, chapter 11, we were given a stress element, and then we were trying to figure out the maximum principal stresses, maximum shear stresses, and then in chapter 11, we try to figure out if under this loading condition we'll observe yielding or not. So now this example actually it gives us a member, and then we have to figure out a failure. So in this example, it says you have this aluminum beam. So we have already given a material. So we know the modulus of elasticity of this aluminum beam is 10,000 KSI, and the yield is 35 KSI. So if we use this material, make a specimen out of it, put it in a machine, apply a uniaxial load, this is what we will get. So under a simple loading case, under the uniaxial simple loading case, we know the yielding will happen when the stresses exceed 35 KSI. So that we know. So we know the material property. We know when material is loaded uniaxially, it will have yielding at 35 KSI. But we don't know if the same material is loaded differently. So now we have a load, this force, and the force is 12 pounds. So now this same material is not loaded uniaxially, right? So now we don't know when this material will yield, like this configuration will yield. So in actual real life scenarios, you have different configuration. You don't only have a uniaxial load, you have different loading conditions. So this is a cantilever beam. It could be a part of a building, bridge. It could be like part of any machine or something. So maybe this is a member, and we want to make sure that this member will not have yielding, or this member will not observe a failure. So that's what we have to figure out in this example. So the length is given, which is 36 inches, right? So we have to figure out if this cantilever beam will have yielding or not. But in other words, will we observe failure of this cantilever beam under this load, which is 12 pounds? So this is what we have to figure out. So we know we can figure out this by yield criteria, right? So this is aluminum. Let's just say this is a ductile material. So this is a ductile material. So we have to use Tresca and von Mises theory to figure out failure. But in Tresca and von Mises, we need to know we have yield, but we need to calculate stress 1 and stress 2, right? So if we know stress 1 and stress 2, then we can figure out failure. But we don't know stress 1 and stress 2. So how to calculate stress 1 and stress 2 in this case? We can calculate stress 1 and stress 2 if somehow we know stress element. So if we know stress element, we can calculate the stress 1, stress 2, and we can calculate the failure, right? If failure will happen or not. But we don't know these stresses, right? These are stress and this is shear stress. We don't know these stresses. How to calculate stresses? We can calculate stresses if we know internal loads. And how we can calculate internal loads? We can calculate internal load by first calculating the reactions. So the first case in this case is part A is draw shear force diagram and bending moment diagram. So that's how we will do. So first we'll calculate shear force and bending moment diagrams. We will get shear force and bending moment. Once we have shear force and bending moment, we can calculate stresses like we did in previous chapters. Once we have stresses, we can extract stresses. So we also have a cross section given. This is a cross section of a, so this is along the length, but if you cut a section, looks from here, so this is how it looks like. So this is a cross section. And we also know the dimensions of a cross section, this is b is equal to 1, this h is equal to 0.5 inches. So this is a cross section. So yeah. So you have a force which is 12 pounds and the length is 36 inches. We know it's a fixed support, so we will have a vertical reaction. So if you do summation of vertical forces, there is only one force which is downward, which is 12. So up also it will have only one force, 12. But you can use equation like you can do summation of f of y is equal to 0. You're gonna get this same thing. And you can do summation of moment is equal to 0. You're gonna get 12 multiplied by 36. You're gonna get 432 pound inch. So these are the two reactions we will get. So now we have to draw shear force and bending moment diagrams. So I'm gonna use graphical method. You guys can use either one. So we'll draw shear force. So we in the start we start with the reaction. So reaction is 12 pound upward. So we'll go 12 pounds up. And then there is nothing from here to here. So since there is nothing, so we're gonna go straight because there is no loading in between. So we're gonna go straight from here. And then we have 12 pound going down. So we'll go down 12 pound. And this is our shear force diagram, which is positive because it was always upward. So that's our shear force diagram. We can also draw bending moment diagram either by using equations or by using graphical method. I'm going to use a graphical method here. So at a start, we see, because this is bending moment, in shear force, in the start we saw reaction, which was 12. In the start, we'll see bending moment, which is minus 432. And it's going to cause hogging, right? So hogging is negative. So we're going to go down 432. And then at every point, we can basically, so for example, if we want to calculate at this point, yes. At this moment is anti-clockwise, right? The anti-clockwise. So how it happens, I know the confusion. So this is anti-clockwise. Anti-clockwise is supposed to be positive, right? But this is negative, right? So how we decide bending moment is, I can write here. So if the beam is gonna bend like this is the case. In our case, this is how the bending will happen because of the load. If you imagine this beam and the load is pushing down, so this is how it looks like, the bending, right? And on the top fiber, you will see tension. And at the bottom fiber, you will see compression. So this whole scenario is called hogging. Hogging is always negative. I don't know. That's how it is. And sagging is always positive. That's the convention we selected. So I'm going to go down in this case because it's causing hogging in the start. So it's negative, and so all you have to do is that at every point you have to add the shear force. So if you do this, you're gonna get something like this. This is negative. This is pound inch. I mean, you guys can go back, revise your shear force and bending moment diagram, but this is how it looks like. Shear force and bending moment. So now we have shear force diagrams and bending moment diagrams. The second part is draw stress distributions. So it says we have to draw stress distribution at x is equal to 0. So this point is x is equal to 0 and this point is x is equal to L. From shear force and bending moment diagrams, we can also see that the shear force is constant along the length, but the bending moment is highest at the start, and then as you go away from the fixed support, then you're gonna see decreasing bending moment. So if you keep on like increasing the load, it's gonna keep on bending, 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 and it will break. But it will break at this point due to bending moment because the bending moment is highest at the start. So if you see some cantilever beam and if you try to pull it at the end, it will always break at the starting point. Why it will always break at the support? Because you have highest bending moment at the, so under shear force it can break at any point, but under axial forces it will always break at the starting point, which is because that's where you will have the highest bending moment and that's where you will have the highest axial stresses. So now what we have to do at this particular point, we have to draw stress distributions along the cross section. So this is our cross section, right? This is our cross section. And we know that this is B is equal to 1 inches. The width of a cross section is 1 inches. The height of a cross section is 0.5 inches. So at this point, we have to draw the stress distribution of a cross section. So how we will do this is figure out what we have at this point. At x is equal to 0, what is a shear force? Shear force is 12 pounds, which is same basically everywhere. Our shear force is 12 pounds. Our bending moment at this point is negative 432 pound inch. That's our bending moment at this point, at x is equal to 0. This is our shear force, and this is our bending moment. So we have to basically calculate stresses because that's what we can compare with the yield criteria. So now we have to calculate stresses. So how to calculate stresses from shear force and bending moment? So from shear force, we can calculate stresses. Shear force will produce shear stresses, and the formula is VQ over IT. Bending moment will produce axial stresses, so the formula is negative MY over I. So once we get these stresses, we can extract the stress element, and from there you guys know what to do, like to calculate the maximum principal stresses, compare it with the yield criteria, figure out if this condition will cause yielding or not. So you guys can try to calculate the stresses along the cross section and draw the distributions like you used to draw before. but you guys understand the flow, right? You have a member, cantilever beam or something with a given loading condition. You will calculate the internal loads, which could be axial load, torsion, shear force, bending moment. From there, you will calculate the stresses. So if it's an axial load, you will go to chapter 3. If it's torsion, you will go to chapter 4. So similarly, you will calculate the stresses. Once you have the stresses, then you can calculate the stress element out of those stresses. Once you have the stress element, then you can do Mohr circle, stress transformation. You can calculate principal stresses and maximum shear stresses. Once you have those, then you can compare it with yield criteria and you can figure out if we will observe failure or if it is safe to put 12 pound of load on this type of cantilever beam under this cross section. So that's the whole flow of everything. So you can draw the stress distributions. You can write down some of the things, some of the formulas. So moment of inertia is bh cubed by 12. Q is a star y star prime. T is basically B, basically 1 inch in this case. And in our case, H is 0.5 inches. This distance is 0.5 inches. This distance is 1 inch. So because of the bending moment, we'll get axial stresses. Because of shear force, we'll get shear stresses. We know that axial stresses looks something like this. So if this is a neutral axis, bending stresses looks like this, and shear stresses looks like this. And since it's a negative moment, so negative moment is hogging, and hogging means tension at the top and compression at the bottom. And shear stress is always one direction. So you have to calculate these values at point A, at point B, at point C. But basically we need the shape. So this point you have to calculate. So if you want to calculate C at C point, the shear stress, so your A star would be, this entire thing would be A star. And from the neutral axis to the center, this point is Y star, right? And this will give us this value just at the center. So you guys can go back and revise everything, but you have to calculate these values. This value, this value, this value, and this value, and this value. So I need values at A, B, and C, and here also at A, B, and C. So I will write down the value. So at this point, we will get 10,368 psi. At point B, we're gonna get 5,184 psi, and at point C, we're gonna get 0. Here at point A, we're gonna get 0. At point B, we're gonna get 27 psi. At point C, we're gonna get 36 psi. So these are the stresses which we will get. So the next step from this is extracting the stress elements from this. So you've got the whole picture, right? You have a You have a member with different loading condition. You calculate the reactions. You calculate the internal loads in terms of normal load, like axial load, torsion, shear stress, bending moment. Once you have those internal loads, you calculate stresses. So once you have those stresses, you draw those stresses along the cross section. Once you have those stresses, now next step we will extract stress element from these values. So once we have those stress elements, then we will do stress transformation and we'll calculate the maximum normal stresses and maximum principal stresses. Once we have those, then we'll compare it with different yield criteria to figure out if this member, this cantilever beam, will experience yielding or not.